Hello, I'm Albert Chu, and I'll be talking about the limits of pan-privacy and shuffle privacy. This is joint work with John Ullman. Our work gives a new lower bound for privately learning parity in the shuffle model. Privately here is in the sense of differential privacy, and the shuffle model is a model of differential privacy that generalizes the local model. The number of samples needed to learn parity is exponentially more than without privacy. The parity learning lower bound is one instance of a general technique. The technique implies lower bounds for other problems, like hypothesis testing, selecting biased coordinate, and sparse mean estimation. The first question we ask is, can we learn about a population without revealing private information about individuals? The answer is yes, we can perform private learning with central differential privacy. Here, users hold data, and they hand it over to an analyzer who computes on that data. The computation satisfies the differential privacy constraint, which roughly means an adversary does not learn too much about any one contribution. This is done by randomization. By definition, the trust boundary encompasses the analyzer. So one question you can ask is if we can perform private learning and estimation without trusting the analyzer. In local privacy, the analyzer is not trusted, and users perform the private computation themselves. They send the output as a message to the analyzer. Because each user contributes noise to a signal, it's very well established that this results in larger error and larger sample complexity. Now, can we avoid trusting the analyzer while retaining accuracy? The shuffle model is similar to the local model in that there is a local randomization and the analyzer is not trusted. However, we also trust a service called the shuffler, which applies a uniformly random permutation to user messages. The goal is to design the local randomizer in such a way that the composition of shuffle and local randomization is differentially private. We'll allow the randomizer itself to be non-private. Recently, there has been a large amount of interest in shuffle privacy. Most have been positive results. Protocols for foundational tasks like summation, histograms, and uniformity testing. There has also been some work on lower bounds. These hold when the randomizer is limited in the number of messages they send. But if we do not limit the number of messages, how many samples are needed to learn parity, for example, in the shuffle model? And we can ask the same question for other problems. To reiterate, our work yields an exponentially large lower bound for parity learning, and we show that these other problems are related and obtain similar results for them. Specifically, when we want to learn with k parities, the lower bound is square root of d choose k, and this is in contrast with the logarithmic lower bound under central privacy. Similarly, hypothesis testing requires root d samples, as does selecting a coordinate with large bias, and sparse mean estimation. In order to get these lower bounds, we'll need to define what differential privacy is. The definition is from the seminal work by Dwork, McSherry, Nassim, and Smith. They are n users in the input. Two neighboring inputs differ by one user's data. And the mechanism M is differentially private if for any pair of neighboring inputs and any outcome of M, swapping between the neighboring datasets changes the odds of that outcome only by a small multiplicative and additive factor. The multiplicative factor is determined by epsilon, which is typically a small constant. The additive factor is delta, which is much smaller than 1 over n. So how do we prove lower bounds? We'll start by defining a helper problem called mixture testing. We'll also define what pan-privacy means. Then we prove our lower bound for pan-private mixture testing. Next, we'll reduce each problem we're interested in to mixture testing. For example, a selection algorithm will imply a mixture tester with roughly the same sample complexity. Our final step is to construct a pan-private mixture tester from a shuffle-private one. Let's first define this mixture testing problem. We are given a family of distributions, and the environment makes one of two choices. It either picks a uniformly random piece of V from the family, or it creates a uniform mixture U. User data is drawn IID from the chosen distribution, and the algorithm has to determine the choice the environment made. Mixture testing has been studied in the local model, for example by Ducci, Jordan, and Wainwright. If a randomizer is locally private, and we have a sample from a uniformly random distribution from the family, the mutual information between the randomizer's output and the identity of the distribution is bounded by a function of the privacy parameter and what we call the infinity to 2 norm of the family. The exact expression of this quantity is a little involved, but for intuition, a loose upper bound is the expected square distance from uniform mixture. We can craft a special family to obtain a lower bound for selection, and also for learning parity functions, and other problems of interest. The main challenge for us is to adapt the technique to shuffle privacy. This is difficult because the randomizer itself is not necessarily private. Now that we've defined mixture testing, let's define pan-privacy. A pan-private algorithm is an online algorithm, meaning that it processes data one at a time. User 1 hands over the data, and the analyzer creates an internal state based on that data. User 2 hands over the data, and the analyzer creates a second internal state. This state replaces the previous state, and the process continues until we reach the final state. At this point, the analyzer outputs some random variable z, and we'll assume that the privacy adversary observes the output, but can also intrude into main memory once. It views a single internal state, S sub I. This models events like security breaches or changes in ownership. And pan-private algorithms ensure that the joint distribution of state and output is differentially private. This must be true for any internal state. Now let's move on to the heart of our paper, a lower bound for pan-private mixture testing. Our goal is to show that any epsilon pan-private mixture tester requires a number of samples inversely proportional to this infinity to 2 norm. And remember, the goal is to distinguish between samples from uniform mixture and a uniformly random distribution from the family. We visualize the two cases in this table. At the top, we have n users all sampling from some random distribution. At the bottom, we have n users all sampling from the uniform mixture. The two cases yield two different outputs, z sub 0 and z sub n. And since we're considering pan-private algorithms, time marches step by step, user by user. Our idea is to show that if n is too small, the distance between the output distributions cannot be large. The intuition is that adding a single user does not offer much information about this index v. But how are we going to show this? We'll use a hybrid argument. We'll start by defining z sub 1, which is the same setup as z sub 0 except user 1 is sampling from the uniform mixture. We'll also have z sub 2, which has the first 2 users sampling from uniform mixture, and so on and so forth. Every z sub I starts with I users sampling IID from uniform mixture, and the rest sampling from a random distribution. Our technical analysis is dedicated to bounding the TV distance between each z sub I minus 1 and z sub I. Then we'll use the triangle inequality to bound the distance between z sub 0 and z sub n. Let's unpack z sub I minus 1 and z sub I. Where does z sub I minus 1 come from? By definition, the first I minus 1 users draw their data from U, the uniform mixture, and any algorithm will create some internal state. There are earlier states, but we don't draw them to save space. Next, user I samples from the random distribution P sub V. The algorithm makes state I based on the sample so far, and the previous state. Then the remaining users sample from the same family as user I. The algorithm will take the state and the data and create the output z sub I minus 1. There are states in between, but I again omit them for space. Now, where does z sub I come from? The process is very similar. The first I minus 1 users sample from U, and the algorithm makes some internal state. But now user I does not sample from a random distribution. It samples from, instead, the uniform mixture. The algorithm makes some internal state based on that sample and the earlier state. Subsequent users sample from uniformly random distribution, and then the algorithm makes an output. The critical point of difference is user I. Basically everything else is the same. Once the algorithm processes user I in the first execution, the state contains some information about V. But in the second execution, the corresponding state contains no information about V. What this means is, intuitively, it suffices to bound the amount of information that state I offers. So we show that the TV distance between the two random variables of interest is bound by the square root of the mutual information between the state S sub I and the index V of the sampling distribution. Once we show this, we can simply invoke prior work because of pan privacy. The state is differentially private, so we can invoke the bound on mutual information from the prior work. Ultimately, we derive the bound epsilon times the infinity to 2 norm, and using a triangle inequality, conclude that the distance between z sub 0 and z sub n is n times that quantity. If n is too small, the TV distance is too small to distinguish between the two cases. Next, we'll have to actually apply our lower bound. We reduce each problem of interest to mixture testing. In the interest of time, I will focus only on one problem, the selection problem. We are given samples from a distribution over the hypercube, and we need to identify a coordinate whose expectation is close to maximum, let's say 0.1. To perform the reduction, we will need to pick a concrete family of distributions. P sub j will be the distribution over the hypercube biased only in one coordinate. The mean is 0.2 instead of 0. For example, when d equals 3 and j equals 3, the top half will have more mass than the bottom half. Our family will be the set of all such distributions, and we can show that the norm of interest is 1 over d, and also that the uniform mixture is uniform over the hypercube. Now let's reduce from selection to mixture testing. For every sample in the mixture testing input, attach a bit of mean 0.1. Pass the inputs into the selection algorithm. If the output is the attached coordinate, which is d plus 1, report uniform. Otherwise, report bias. This reduction works because if the input distribution is uniform, the mean of the attached bit is larger than the rest by 0.1. So the selection algorithm will identify it. On the other hand, there will be bias in some other coordinate, so it will dominate the rest by at least 0.1. Again, the selection algorithm will identify it. So that was how to obtain a lower bound for selection, but similar steps and constructions yield lower bounds for other problems of interest. Our final step is to transform a shuffle private mixture tester into a pan private one, so that our lower bounds will carry over. The following is a corollary of joint work with Balser, Joseph, and Mao. If we have a shuffle protocol for mixture testing with sample complexity 3n, then we can create a pan-private algorithm of sample complexity n. All of our lower bounds will carry over except for some change in constants. Our pan-private algorithm will have 3 phases: initialization, reading, and a final phase. We start by running the randomizer on a sample from the uniform mixture, then store the messages in random places in main memory. We repeat this n times. Main memory now consists of randomly positioned randomized messages. Now we move on to the reading phase. We run the randomizer on the first user's data, and then write the messages to random places in memory, and repeat it for the rest of the users. The final phase is identical to the initial phase. We run the randomizer on samples from the uniform mixture. The output of the algorithm is determined by running the protocol's analyzer on the final state. And the final state is S sub 3n because we have 3n data values. We have to argue that this online algorithm is pan-private. Intuitively, this is because any state is generated by running the shuffle protocol. So if the adversary intrudes right after user 1 is read, the initial phase ensures that he'll only see a set of messages shuffled from n executions of the randomizer. We can then invoke the privacy of the shuffle protocol for n users. Now the final phase compensates for the fact that the adversary also sees the output of the algorithm, but that's a technical detail you can look at in our paper. We've argued that this simulation is pan-private, but how accurate is it? Notice that the output is equivalent to running the shuffle protocol on the real samples, mixed with a bunch of samples from a uniform mixture. This means that we're running the protocol on what looks like a dilution of our original distribution with the uniform mixture. This does not affect our asymptotic bounds. To see why, recall our family distributions for a selection problem, which concerned the hypercube. The diluted distribution and the original distribution only differ by the amount of bias towards J. So this shifts the results and constructions by a small constant factor. So to sum up, our work yields new lower bounds for shuffle privacy via pan-privacy. Our results hold without limiting the communication from users. And again, we've established the limits of 2 models of private computation. Pan and shuffle privacy are not appropriate for the problems we identify, but they remain good alternatives for other simpler problems like summation and histograms. There are questions that can be explored deeper. For instance, can we use space complexity or communication complexity to get alternative lower bounds? Another avenue of research is enhancing the shuffler. It's possible that a shuffler which erases or adds messages could enable more powerful computations. Finally, the space between pan-privacy and central privacy is a little unclear. Are there other natural models that lie between the two models? Thank you for watching this video.